right. Thank you all for joining our second seminar of the term. Today we have Professor Stefania Fresca, who's joining us this term at the University of Washington. Previously, she was at Politecnico di Milano over in Italy, and actually just did a research stay at Cambridge University in the UK. And today she'll be talking to us about machine learning and partial differential equations. And with that, I'll let you take it away. Thank you, Stefania.
Thank you, Nick. Thank you for the nice introduction and for inviting me here today. Today I will talk mainly about complexity reduction techniques or reduced order models for the efficient solution of parameterized nonlinear time-dependent PDEs. But before going into details, I would like to give you some overview and some context about my research and the research of my lab. We focus on scientific machine learning, and SciML is the field which employs machine learning algorithms to accelerate, enhance, or even enable the solution of problems described by means of differential equations in engineering applications. In particular, we focus on three main areas: surrogate modeling, optimal control, and multi-scale optimization and integration. But during this talk, I will mainly focus on surrogate modeling and on a particular kind of surrogate modeling, which is reduced order modeling. So I will start by briefly introducing deep learning-based reduced order models. They are nonlinear, non-intrusive techniques for the efficient approximation of parameterized PDEs. And I will also show you some results related to an industrial application, which is related to the approximation of the behavior of microelectromechanical systems of MEMS. Then I will move to an extension, pre-train physics-informed DL-ROM. In this case, what we did was to employ a physics-informed loss functional to compensate for data scarcity. And it is also provided with an efficient training strategy consisting of pre-training plus fine-tuning stages. Finally, the last topic is related to continuous geometry-aware DL-ROM. In this case, we use a space-continuous formulation to account for multi-resolution dataset that is very important if we want to handle geometrically parameterized problems. The basis functions in this approach are aware of the geometrical parameterizations, which enables us to improve the performance. So everything will be clear in some slides. But let's start from the motivation of reduced order modeling. Several tasks in scientific computing, such as the solution of data assimilation, optimal control, parameter estimation, uncertainty quantification problems, performing model-based simulations, or the implementation of digital twins, they rely on physics-based high-fidelity models, parameterized nonlinear time-dependent PDEs usually. But in order to carry out all these tasks, the repeated computation of the PDE solution is required, which makes the use of full-order models, such as the finite element method, computationally prohibitive. Lots of effort has been done in the last year in order to develop surrogate models and reduced order models exploiting deep learning algorithms. Here, the goal is to replace the FOM by a model showing much lower complexity but still accurate, by exploiting from one side the reliability of numerical data and from the other side the efficiency of deep learning algorithms. So, the goal of reduced order modeling is the efficient approximation of the parameters to solution map. And if we want to build a ROM, we have to perform two main tasks. The first one is the computation of a suitable trial manifold approximating the solution manifold, which is the set of all the PDE solutions by varying time and parameters. Once we have identified the trial manifold, then we can identify or take care of identifying a latent representation embedding the reduced dynamics onto the trial manifold. In traditional linear ROMs, such as POD-Galerkin ROMs or the reduced basis method, we look for an approximation of the form solution expressed in terms of basis functions as a linear combination of basis functions. V is a matrix. We can, for example, compute it by means of POD, and UN are the ROM intrinsic coordinates. The solution manifold is approximated by a linear trial manifold defined in terms of the matrix V. Obviously, the function mapping the low-dimensional intrinsic coordinates to the high-dimensional ROM approximation is linear, and the reduced dynamics is described by means of a parameterized dynamical system which has a dimension smaller than the form dimension, obviously. The point here is that for any new instance of the parameters, in this setting, we need to solve a dynamical system. A nonlinear ROM instead looks for an approximation of the form solution defined in terms of a nonlinear function pch. This nonlinear function defines the nonlinear trial manifold, and obviously, the function mapping the low-dimensional intrinsic coordinates to the high-dimensional ROM approximation is nonlinear. But in our case, this function has to be learned. Finally, the reduced dynamics is described by another nonlinear function. Again, it has to be learned, which directly models the relationship between the parameters and the intrinsic coordinates. This relationship was instead intrinsic to the ROM equation in the previous setting. On this framework construct a DL-ROM. Here I reported the architecture. We have three main blocks. The encoder function, the deep feed-forward neural network, and the decoder function. So the decoder is responsible for the modeling of the nonlinear trial manifold. The deep feed-forward neural network is the reduced network, so it's responsible for describing the reduced dynamics. In order to train a decoder, we also employ the encoder function. The composition of these two functions provides us the autoencoder, and it also, in our case, employing the encoder function stabilizes training. So very briefly, let's look at the flow. The form solution enters the encoder function, and we obtain a low-dimensional representation of it. The same parameter instance associated to the form enters the deep feed-forward neural network, and we obtain the latent variables or intrinsic coordinates. In this way, the error between the two low-dimensional vectors is accumulated. The latent variables enter the decoder, and we obtain the ROM approximation, thus the reconstruction error is obtained. Obviously, the encoder function is just used during the training phase. At testing time, we discard it. Several benefits are associated to the use of ADL-ROM, such as it can be queried at any time instant without requiring the solution of a dynamical system until that time. The time resolution it needs is usually larger than the one entailed by the solution of dynamical systems, and there are others. But there is a main issue, a main drawback, which is it depends on the form dimension. And this may lead to long training computational times when we are dealing with large-scale problems. So in order to overcome this issue, we extended this architecture to the POD enhanced version, where now the goal is to approximate the intrinsic coordinates, and the, for example, loss function becomes the one into the slide. So POD DLROM makes the training phase extremely fast, thanks to a prior moderate dimensionality reduction achieved, for example, by means of our SVG. I want to highlight moderate reduction because we are not using POD in this context to match the intrinsic dimension of the problem. We are just using it as a prior filter. Obviously, the POD DLROM takes as input the intrinsic coordinates, the coefficient of the POD basis modes, and of the POD basis functions, and provide an approximation of them. We have applied this architecture on a very broad range of examples. For example, cardiac electrophysiology, the modeling of the electrical activity of the heart. Here I reported a realistic geometry of left ventricle and left atrium, and the parameter is the conductivity in the fibers direction. That is, the capability of the tissue in propagating the electrical signal through the myocardium. Again, here, by using POD DLROM, we are able to drastically decrease the training time and to provide a real-time solution at testing time. Then the numerical blood flow in a cerebral aneurysm. The parameter-dependent inlet flow rate profile is the one provided in the slide. And here, the key thing is that POD DLROM is able to capture both the flow recirculation and the blood stasis into the bulge. If these two examples are related to a life science domain, we also employ it in an industry-related task, which was connected to the approximation of the dynamical response of MEMS. Microelectromechanical systems are micro devices combining electrical and mechanical components, and resonators, gyroscopes, micromirrors are all examples of MEMS. In particular, micromirrors are witnessing an explosive growth in recent years due to successful applications ranging from LiDAR in autonomous driving or as projectors of virtual content onto the lenses employed in augmented reality or mixed reality tasks. MEMS must satisfy industrial requirements which reflect on the numerical solution of these systems. For example, the complexity of the geometry results in a high dimensionality of the foam. They are characterized by large quality factors, which entail long transients, and this means that the system must be solved for a very high number of time instances before reaching the steady state, which is the interesting part. The presence of strong nonlinearities requires the use of a small time step size. The dynamic response is usually characterized for varying the input frequency and the input signal amplitude, so they need to compute an output of interest, which is the frequency response function. Finally, these devices undergo large transformations, which are modeled by means of inertial and geometric nonlinearities, which turn the behavior of the FRF in an hardening or softening behavior. And this means that the solution is no more unique in some frequency regions, so bifurcations require special treatments. In this context, we dealt with the approximation of the behavior of a MEMS micromirror. The high accuracy obtained in the reconstruction of the displacement field by means of the POD DLROM enables us to compute the frequency response function for increasing values of beta where in this case, the control variable is the rotational angle of the plate of the micromirror. And here I want just to remark that in order to compute 60 million of testing parameter instances, we need less than 2 minutes. And such short times are of primary importance if we think about design optimization or online control tasks for MEMS. Then we move to a multiphysics problem. We wanted to reconstruct the electromechanical behavior of a MEMS gyroscope. In this case, the foam snapshots are obtained by commercial software provided by Coventor. And the behavior of the solution is mainly related to the red bullet, let's say. This is the drive mode. We have this expansion and relaxation in the vertical and horizontal direction, except for a frequency interval in which a second mode activates and it starts to interact with the previous mode. This second mode is the sense mode. So these two modes are coupled and they mainly describe the dynamics of the system. And this can be seen as a first reason in order to understand why, from a reduced order modeling point of view, at least two latent variables are needed in order to be able to reconstruct the dynamics. Indeed, using just one latent variable was not enough. We were not able to, basically, as you can see, to capture the FRF. So I show you these techniques, DL-ROM, POD, DL-ROM. They perform well. And in the case in which you basically have data, you are interested mainly in interpolation task, in distribution task, and you don't want to deal with geometrical variability. But as soon as you want to address one of these issues, what I show you up to now is not enough. So we had to properly extend these techniques to kind of overcome these issues. This is what we did in part by means of pre-trained physics-informed DL-ROM. In this case, we wanted to exploit all the physical knowledge we have about the system in order to compensate for data scarcity, small data context, and enhance generalization capability, especially in extrapolation tasks. Scientific machine learning does not pertain a big data context, but rather a small data interpolation or a small data extrapolation context. In the first case, we sample scattered data from the entire time parameter domain, thus leaving a large portion of it substantially uncovered by training data. In the second case, we draw snapshots from a very small region of the entire time parameter domain, and so there is the total absence of data in an extended portion of it. However, we all know that the reliability of neural networks strongly depends on the amount of data they are fed with during the training procedure. So in order to overcome this limitation, several techniques in the literature, as the one I'm going to show you now, make use of the physics-informed assumption. The different terms underlying the governing equation, the governing physical laws, convey the same information of the data synthetically generated from them by means of high-fidelity solvers. On this main assumption, we are going to build all the PTPI DL-ROM. And its main key aspects, its main features are a space-continuous architecture, which enables a mesh-agnostic prediction, a physics-based loss functional, which compensates for data scarcity in the context I just showed you, an efficient pre-training strategy which enables us to accelerate the training phase and promote convergence to suitable minima. And finally, a fine-tuning strategy, which further enhances the prediction accuracy. Let's start from the first one. POD plus DNN architectures, as the classical POD DL-ROM, are limited by their discrete nature. This means that they cannot be evaluated continuously in space. Space continuous architectures, they try to fill this deficiency, and DPONet are the main example of a space continuous architecture. In this case, the basis functions are approximated by means of a neural network referred to as trunknet. By combining the outputs of the branch net and the trunknet, we are able to obtain a mesh agnostic approximator, meaning that its predictions are not limited to the vertices of the mesh, or in the same way, the reduced solution, the approximated solution, can be evaluated at any given point in the space domain. In order to build such a mesh-agnostic approximator, what we did at this point was to merge POD-DL-ROM with DPONet. In particular, the branch net architecture is instantiated as a DL-ROM, so it provides a set of parameter and time-dependent coefficients, while the trunknet is constrained to approximate POD modes. Thanks to such a mesh-agnostic approximator, we are able to employ a physics-based loss functional, which is based on the strong continuous formulation of the PDE residuals. If we use for the approximated solution the definition in the formulation in terms of the trunknet's basis functions, then the PDE residuals for both internal and boundary points are the one reported. However, the evaluation of possibly high-order space derivatives remain the main computational bottleneck in the residual computation pipeline, especially when we are dealing with very deep neural networks. So in this respect, we performed a preliminary test in which we wanted to analyze AD computational time, the time needed by automatic differentiation, with respect to the complexity of the trunknet, width and depth, and the derivative order. The higher the derivative order, the higher AD computational time. AD computational time does not depend on the width, but they depend on the depth of the trunknet. Especially in the case of a second-order derivative, you can see that the trend is very steep. So, derivatives are computed at training time and during the training phase. And in this way, the training computational time can easily grow when we are dealing with high-order derivatives or very deep trunknet. So we needed to devise a training algorithm, a strategy, in order to limit the computational burden associated to the residual computational pipeline. We did it by means of a training procedure composed by pre-training plus fine-tuning stages. This is our way to solve the computational bottleneck. More precisely, we have the first step of pre-training. We compute POD basis functions by means of the available supervised data. We freeze the branch network, and we train the trunk network to approximate POD basis functions in a supervised way. The second step of pre-training, this time we freeze the trunk network. We pre-compute the space derivatives and we store them. And then we train the branch network with the loss functional blending physics and data. Finally, the fine-tuning stage in which we train the entire architecture by means of the physics-informed loss functional for just few epochs. Numerical examples. In this test case, we want to assess the parameter extrapolation capabilities of PTPI DL-ROM. In doing that, we compare POD DL-ROM with two solutions obtained by means of PTPI just after pre-training and with fine-tuning. We can see that the total absence of data, of supervised data, in the neighborhood of the testing parameter instance prevents POD DL-ROM in providing a reliable accuracy, a reliable approximation. Instead, with PTPI, already after pre-training, we obtain an accurate solution, basically. Then, by means of fine-tuning, we are able to decrease the testing error, to halve the testing error. We also performed an ablation study with respect to the number of supervised data provided during the training phase. In the interpolation regime, the pink red box, as soon as the number of labeled data provided during the training phase decreases, the gap between the two techniques in terms of performance, I mean between POD DL-ROM and PTPI, increases. Then, in the extrapolation regime, POD DL-ROM simply diverges. PTPI instead is able to preserve a constant testing accuracy over the entire parameter space. Then 3D advection diffusion reaction equation with a sinusoidal forcing term. We reported the distribution of the error, of the testing error with over the parameter domain. And PTPI DL-ROM is the approach providing the best accuracy, especially after fine-tuning, with fine-tuning. Then we wanted to assess the effectiveness of our proposed training strategy. And in doing that, we compare it with the two alternative procedures, no pre-training, and pre-training with just supervised data, vanilla pre-training. And as we can see, PTPI DL-ROM is the one providing us the lowest testing error in the smallest amount of epochs, and it also shows the most stable training. Finally, the solution of the incompressible Navier-Stokes equations on a backward-facing step geometry. PTPI is able to preserve the accuracy also in the time extrapolation regime. Instead, a data-driven technique, just a data-driven technique like POD DL-ROM, it's not. Basically, the testing error here starts to increase just beyond the end of the training time window. Now, I would like to move to the last approach I want to show you. Continuous geometry-aware DL-ROM. In this case, we want to address the solution of geometrically parameterized problems by leveraging geometry-aware basis functions. That is a geometry-aware dimensionality reduction framework cast in an infinite dimensional setting. The general formulation of a PD problem characterized by geometrical variability is the one shown, where n is a generic nonlinear operator, B enforces boundary conditions, and U0 denotes the initial data. I want to remark that for any instance of the geometrical parameters, the solution field belongs to a different domain. And if we want to build a ROM in such context, we have to deal with two main issues. The first one is related to the fact that the majority of ROM techniques in the literature rely on a space-discrete formulation, which limits the range of application just to diffeomorphic meshes with the same resolution, with a fixed resolution. Then the second point is the lack of a suitable inductive bias, which is tailored for geometric variability. This means that we have to find an effective way to embed the geometrical parameterization into our reduced order model. To solve these two issues, we designed and developed CGA. And in order to give you some insights and intuition behind it, I would like to start from the discrete POD. So the POD, for a given number of modes, the POD subspace minimizes the error between the snapshots and their projections onto the POD subspace. This is well known. The snapshots have to share the same number of degrees of freedom. This means that they have to belong to a fixed resolution dataset. However, there are domains for which, while there are domains for which a fine discretization is needed to capture the low effects, the low scale effects of the physical problem, there may be other configuration of the domain that just require a coarser discretization to grasp the underlying physics. So there is the need to be able to handle multi-resolution dataset. And in doing this, we move from the discrete POD to the space continuous one. The POD basis functions are now continuous in space. And the optimality criterion, the optimality property of POD is casted in a suitable functional space or in a suitable infinite dimensional setting. But also at the continuous level, we still have a problem. In the POD optimization, geometrical and physical parameters play the same role, even if they usually induce different effects on the variability of the solution manifold. Indeed, a slow decay of eigenvalues is usually associated to the geometrical parameterization. Instead, the physical parameters, they just have a marginal contribution. But in this context, one has to select a large number of POD basis functions to capture the variability of the solution manifold, and this results in inefficiency and high computational cost. In order to mitigate such inefficiency, we proposed continuous geometry-aware modes, a set of basis functions that for any given instance of the geometrical parameterizations, they are optimal for this for this choice of the geometrical parameterization. That is, we impose a strong inductive bias by making the basis functions aware of the geometrical parameterization. So now the question is how to actually compute these basis functions, the CGA basis functions. To answer this question, we need some math. I'm sorry. We start from our original problem. We need to define an abstract functional setting in which is possible to address the dimensionality reduction task, which is not possible to address in this space because here the solution manifold is not well defined. So we perform a change of variables which cast the original problem, the original differential problem, onto a reference configuration which doesn't depend anymore on the geometrical parameters. In doing this, we employ a special mapping Z characterizing the deformation from the original configuration to the reference domain, and vice versa, obviously. And to do that, we need to require sufficient smoothness to Z and its inverse. But the point is that now, in this space, in this functional space, it is possible to have a solution manifold which is well-defined. So we are on the reference configuration. We want to solve the CGA optimization problem. And by solving it, we obtain CGA basis functions, a set of global basis functions defined on the reference configuration, depending on the geometrical parameters, and in particular, for any given choice of the geometrical parameters, they are optimal. Now, we use again the change of variables formula to obtain an alternative definition of the CGA basis functions, which is just more suited to our need. But there is a tricky point here. This collection here is usually not available in a closed form. So we decide to model it by means of neural networks. And whose goal is the goal of this neural network is to provide a geometry-aware, finite-dimensional representation of the infinite-dimensional solution field by optimizing as a loss function the cost functional of the CGA optimization problem. Now, the final architecture in which we cast CGA basis functions into the DLROM context is the one here. I want to remark that CGA basis functions are trained in an unsupervised way, and as in traditional DLROM, at testing time, we discard the encoder function. Now, before moving to the numerical results, I want just to spend some words on the compressive capabilities of CGA basis functions. In the table, I summarized the optimization problem features of POD and CGA. So, POD gives us optimal basis functions on average, because it doesn't distinguish between physical and geometrical parameters. CGA provides instead us a set of basis function given optimal for the given instance of the parameters, of the geometrical parameters. It can actually be proved that if we consider the best approximation error, and if we consider the same reduced dimension n, CGA basis functions outperforms POD modes. But again, it's not possible to compute the optimal CGA basis function. They are not available in a closed form. So we model it by means of neural networks. And it can be shown that there exists a neural network for which a quasi-optimality property holds. So all this to say that CGA basis function usually enables us to use a smaller number of basis functions with respect to POD modes in order to capture the variability of the solution manifold, and this enables us to use light architectures. Let's start with the hyperelasticity test case. This is a common benchmark for a geometrically parameterized problem. It was proposed in the GEO FNO paper. And we wanted to use it in order to compare CGA DL-ROM with several baseline in the literature. The goal is to reconstruct the stress field on a geometry made of a points cloud, and the geometrical parametrization describes the topology of the void. So CGA DL-ROM showcases showcases comparable accuracy with the other baselines in the literature, but it is the one providing the lightest architecture. The architecture with the minimum number of weights and biases. The approach providing the best result in terms of accuracy is GNOT, at the cost of a very heavy architecture since it is based on transformers. The approach which shows a comparable number of weights and biases to the ones of CGA DL-ROM is Coral, but it performs worse. It has worse performance, and it also requires an inference time optimization because it's based on implicit neural representation. Finally, if we consider DeepNet, it's clear that endowing the basis functions with geometrical awareness is effective in reaching better accuracies. Then on this slide, there are the ground truth data together with the basis functions, both on the original and reference domains for two testing parameter instances. And you can see that the basis functions are deeply connected to the local features of the solutions of the solution field that the solution field exhibits in proximity of the void, which is obviously the area in which the geometrical parametrization is more intense. Then Navier-Stokes, or the flow around an obstacle test case. We have two geometrical parameters. One is the y coordinate of the center of the obstacle, and then the radius, plus two physical parameters, the maximum amplitude of the inlet profile and the viscosity coefficient. And here, CGA-DL-ROM is able again to capture the low-scale effects in the obstacle's wake, where this is the area in which the geometrical parametrization is strongest. Then we performed an ablation study with respect to the number of geometries provided during the training stage, and by halving them at each step. The scaling law is almost linear, and this means that CGA-DL-ROM is able to take advantage of the augmented information to reach a better accuracy. Finally, an industry-related test case. We want to predict the temperature field of a fluid flowing in a 3D heat exchanger. We have 14 geometrical parameters for the heat exchanger plus 6 physical parameters. And the two columns of the solution refers to the comparison between the prediction and the ground truth data for two different testing parameter instances. And CGA-DL-ROM is able to capture the moving fronts of the temperature field, which are induced by the advection field. So, concluding, we started with a general introduction, then we moved to PTPI DL-ROM, pre-trained physics-informed DL-ROM. It integrates the limited available data with the underlying physical laws to achieve a reliable approximation in small data context. It also uses an efficient training procedure in order to mitigate the computational burden associated to physics-informed paradigms. Continuous geometry-aware DL-ROM leverages a space continuous formulation to account for multi-resolution dataset, thus enabling us to handle geometrically parameterized problems. It exploits geometry-aware basis function to enhance the compression capability as well as the performance, the overall performance of the approach. So the two techniques I show you have mathematical tools, let's call it, like in pre-training physics in 4DL-ROM, the physics-based loss functional or the training procedure, and in CGA DL-ROM, the construction of the CGA basis functions that we chose to cast them into the DL-ROM context, but these are general mathematical tools that can be used with different architectures from the one I presented today. And with this, I would like to thank you for your attention, and I'm happy to answer possible questions.
Thank you so much for that talk, Stefania. Are there any questions in our audience, and also monitoring Zoom as well?
I'm wondering what numerical method you can make your data for the EPI DL-ROM cases. And also, if you're using FEM or FBM or something like that, when you're sampling collocation points for your training data, is there a bias in the way that you formulate your shape function, and does that lead to biases in the model to not generalize to other shape functions?
Wait, okay, we use FEM.
Can you repeat the question also?
Yeah, but so the first part I understood it was which kind of numerical methods we use for the numerical result in PPI, right? And then when you were talking about shape functions, I didn't get it.
So when you're sampling points for training your data for a continuous model, is the way that you sample those like from collocation points, or are there
Yeah, for sure they have to be, let's say, mesh points, or you can also interpolate on new meshes. That's not a problem. You can be quite flexible on that. And yes, we use finite element methods basically.
So my question is does that like the shape functions that you choose and how you sample your data, does that
No, not really, because I mean it's done at the same time. Since it is a space continuous architecture, we can actually test it on different points, and it seems that there is the generalization performance, the generalization capabilities are robust from this point of view.
Thank you.
Because I'm not sure we did it in the examples I show you, but a possibility is also to randomly select them during the training and maybe change it, I don't know, every epoch or every number, after a fixed number of epochs. Yeah.
Geometry. Do you have any understanding of the scale as you go to geometrical parameters? So you start off with something maybe, okay, I can adjust 2 parameters. Flow physics was, your position, the aspects of the geometry. Then you go to 14. Do you understand, like, if I go from 2 to 4 to 8 to 16 in terms of dimensions of C, what you have any even rough estimate of what the scaling law is to that?
I mean,
Can you repeat it for the Zoom? Sorry.
yeah. If there is if I have any insight on the scaling laws with respect to the increasing number of geometrical parameters, actually, to give you an answer, we should have run this kind of test on the same examples, which we didn't. So I have no idea, but what I can say is that all the examples we show have a number of weights and biases, which is always around between 300,000 and 700,000, always below the million, okay? But starting from this estimate and being able to give you a scaling law, no, I'm not. We should try to run the same experiment, I mean, the same physics basically, by increasing the number of geometrical parameters.
If you don't mind, I have to follow up. Follow-up with that would be also to, I think an assumption there is also that if you don't change the geometry parameter, let's take one of the parameters in C, like C1 and I vary it, that if I vary it, that the solution is sort of changing smoothly versus I can go through a bifurcation. Because I can imagine you could say, I changed the geometry parameter, but now I'm in a bifurcated regime. So the dynamics is totally different just from a normally we think about this as sort of like change some other property, but now I'm thinking about changing the geometry to induce the bifurcation. Am I right that you're kind of making an assumption that it must be somewhat smooth?
Yeah, definitely.
Okay. Great, thanks.
At least for the mathematical formulation behind it, yes.
Okay.
Then for sure you will need lots of data in order to be able to model it, or some physical inductive bias. But for the theoretical mathematical background, yes, you cannot deal with that.
There's a question on Zoom. Could you point us to a simple or illustrative example on which these methods have been implemented? This would be helpful for a novice who may want to use these methods.
I mean, if you mean code examples.
I'll let Mohammed respond here if that's what.
Okay.
Code would be helpful, but I more generally meant like a simple PDE where these have been. Examples you showed are very impressive and complicated, but those.
Okay, look at there are. I mean, these two approaches are related to the two different papers. In each of them, there is the first example is kind of a toy problem, which I didn't present today. And for each of them, there is also the GitHub repository. So if you want the code, there is also this one. If you just look at the paper, there are two simpler examples, which I didn't show.
Wonderful, thank you.
You're welcome.
Any other questions in the room or on Zoom? Okay, I have one last question maybe to kick us out then. Take us out, not kick us out. For now that you've like done this like geometry aware like ROM building, have you also looked at sort of an inverse problem of finding the optimal geometry that, you know, for a particular optimization, right? Like for that last example that you gave, you have these, was it like 1626 parameters that define that heat exchanger? Is there like a most efficient heat exchanger based off of those?
Yeah, no, we didn't try, but for sure that's, I mean,
Okay.
one future development we are thinking about. And the point is that what is really missing in CGA is that you can just handle geometries which is possible to physically parameterize. You cannot handle shape directly.
Right.
Okay. So once we can embed this shape encoding, which we are doing, I think that this could be perfect to go in your direction.
Okay, great.